Good morning, students. Our today's topic is compactness and finite dimensions. A few other basic properties of finite dimensional normed spaces and subspaces are related to the concept of compactness. So, first of all, we define what is compact metric space. Let a metric space X, we say that this metric space is compact if every sequence in X has a convergent subsequence, or we can say that this metric space is sequentially compact. Next definition is, in what condition we say that a subset of metric space is compact. So a subset M of X is said to be compact if M is compact considered as a subspace of X. It means every sequence in M has a convergent subsequence whose limit is an element of M. So if this condition holds, we say that the subset M of X is compact. Now, a general property of compact sets is expressed in the following lemma. A compact subset M of a metric space X is closed and bounded. So let us take X be a metric space and M be compact subset of X. So firstly, we will prove that M is closed. In order to prove that M is closed, we show that M is equal to M closure. Now because every set is contained in its closure, so M is contained in M closure. Therefore, it remains to show that M closure is contained in M. So let us take an element X belongs to M closure. It means X is closure point of M. So by definition, there exists a sequence in M which converges to this element X. So let us take that sequence is denoted by the sequence Xn. Now we are given that the set M is compact. Therefore, by definition, the limit of convergent subsequence of any sequence in M that will also be an element of M, and therefore X will also be an element of M. Thus we have proved X belongs to M closure implies that X belongs to M. It means M closure is contained in M. So combining the two parts, M is contained in M closure and M closure is contained in M. So this implies that M is closed. Now it remains to prove that M is bounded. We will prove it by contradiction. Let if possible M is not bounded. If M is not bounded, then it would contain an unbounded sequence, say the sequence Ym, such that the distance of any fixed element of M from every member of this sequence Ym that will be greater than M for every M belonging to the set of natural numbers. That fixed element of M we have taken as B. The distance of this fixed element B from the members Ym of the sequence that will be greater than M. And clearly, this sequence will not have any convergent subsequence because every convergent sequence is bounded sequence. So if we suppose the sequence Ym has a convergent subsequence, say a Ymk, then that subsequence must be bounded. But that will be a contradiction because the sequence Ym is unbounded. So this contradiction proves that M is bounded. Thus we have proved that the compact subset of a metric space is closed as well as bounded. Now we show that the converse of this lemma is generally false. It means every closed and bounded subset of a metric space need not be compact. This result is true only for the finite dimensional spaces. We will give an example to show that the converse of lemma is false in general. Let us take the example of the space L2 space, and we consider a sequence denoted by the sequence En, and let M be the set consisting of the members of the sequence En. Here the sequence En has the members denoted by delta Nj. Here del Nj that denotes the Kronecker delta function. Here the nth term is 1 and all the other terms, those are 0. It means Ei is a sequence whose ith entry is 1 and all the other entries are 0, and the norm of each Ei is 1, and therefore we can say that the set M is bounded set. Now we show that M is closed. In order to show that M is closed, we will show that the sequence formed by the members Ei that has no limit point, and then obviously M closure will be same as the set M. Now if we consider the set of the terms of the sequence Ei and remove the repeating terms, we can see that M has no limit point, and therefore M closure that will be same as M. So we have proved M is closed as well as bounded. Now also the sequence En, because the sequence has no limit point, means M has no limit point, and therefore the sequence En that will have no convergent subsequence, and therefore for this reason M is not compact. So this is an example of closed and bounded subset of a metric space which is not compact. However, this result is true for finite dimension normed spaces. So in case of finite dimensional normed spaces, we have the following theorem. In a finite dimensional normed space, a subset M is compact if and only if it is closed and bounded. So let us take X be a finite dimensional normed space. Every normed space is a metric space, so X is also a metric space. Let us take M be the subset of X. Now because if we take M is compact, then by the lemma which we have discussed, by that lemma M will be closed and bounded. So you will have to prove that lemma in the first part of this theorem. Now we'll prove the converse part. Now conversely, we are given M is closed and bounded, and we have to prove that M is compact. It means we prove that any sequence in M has a convergent subsequence. Now because X is finite dimensional, so let us take the dimension of X is n, and so we can take a basis consisting of n vectors and say that basis is given by the set consisting of the vectors e1, e2, e3 up to en. This we have taken as a basis of X. Now let us take a sequence in M denoted by the sequence xm. Now because each xm belongs to the set M, and therefore M is a subset of X, therefore each xm can be written as a linear combination of the vectors e1, e2, e3 up to en. So we have denoted the vector xm by this linear combination. Now because M is bounded also, it means the sequence xm, that is bounded sequence in M. So we can use the definition of boundedness. So by definition of bounded, there exists a positive real number k such that the norm of each xm will be less than or equal to k, and this is true for every m belonging to the set of natural numbers. Now here because E1, E2, E3, En that forms the basis of X, and therefore this set is linearly independent. So we can use the linear combinations lemma. Now from here, because k is greater than or equal to xm norm, substituting the value of xm here and using the linear combinations lemma, we have k is greater than or equal to c times the sum of the mod of the scalars exile im. So from here, taking c in the denominator in the left side, so we get summation exile im mod that is less than or equal to c for every m belonging to set of natural numbers. From here we can see that the mod of exile im that is less than or equal to k by c, and this is true for every I which is varying from 1 to n, and m is a natural number. So this proves that the sequence formed by the scalars exile im that is a bounded sequence in the field k. K is the field of scalars. For I is equal to 1, this will become exile 1m that is a bounded sequence in k. So we can use Bolzano-Weierstrass theorem. According to that theorem, every infinite and bounded sequence has a convergent subsequence. So this sequence will have a convergent subsequence, and let us take beta 1 be the limit of this subsequence, and we consider the corresponding subsequence of the sequence xm, and that subsequence we have denoted by the sequence x1m. Now we can use the same argument again and again. This will again have a subsequence x2m for which the corresponding sequence of scalars exile 2m that is convergent, and let us take beta to be the limit of that converging subsequence. We can continue in this way, and after n steps we get a subsequence xnm of the sequence xn whose elements are of the form of the linear combinations consisting of the vectors e1, e2, e3 up to en. All this process we have already discussed in the linear combinations lemma. Now we have to prove that this subsequence that converges to a point of m. Now we can consider the norm of xnm minus y. Substituting the values of xnm and y is formed by using the n limits beta 1, beta 2, beta 3 up to beta m. So we're substituting the values here, and using the same process as we used in linear combinations lemma, we can say that the sequence xnm that converges to y. Here y is beta 1 e1 plus beta 2 e2 and so on up to beta n en. Now because m is closed, and by definition of closed, a set is closed if and only if every sequence in M which converges to X, then that X belongs to M. So here, by using the closed property of M, we can say that this limit of the sequence Xnm that will also be an element of M. So Y belongs to M. Thus we have shown that every sequence xm in the set M has a convergent subsequence in M. So this proves that M is compact. So this was one of the property of finite dimensional normed spaces.